The universe, on its grandest scales, appears serene and unchanging. But within the vast, dark voids between the stars, a slow and relentless process unfolds. It begins in places of profound cold and emptiness, inside what astronomers call giant molecular clouds. These are not clouds in the terrestrial sense, but immense, sprawling structures of gas and dust, hundreds of light years across, with masses millions of times greater than our own sun. Their temperatures hover just a few degrees above absolute zero, cold enough for molecules, primarily hydrogen, to form and drift in a delicate, near-perfect equilibrium. For eons, such a cloud can exist in this state, a placid reservoir of cosmic potential, where the gentle outward push of gas pressure perfectly balances the persistent inward pull of its own gravity. The birth of a star requires that this balance be broken. The trigger is often an external disturbance, a cosmic nudge that compresses a region of the cloud and gives gravity the advantage it needs. This catalyst can be the shock wave from a distant supernova, the explosive death of a massive star, which sends ripples of energy and matter hurtling through the interstellar medium. It might also be the gravitational influence of a passing star, or the sweeping pressure of a galaxy's spiral arm, a density wave that slowly moves through the galactic disk, compressing gas and dust as it goes. Whatever the cause, a section of the cloud begins to collapse, a slow-motion fall inward that will span hundreds of thousands of years. As the material gathers toward a common center, its gravitational potential energy is converted into heat, and the core of the collapsing region slowly begins to warm. This large collapsing cloud does not simply form one enormous star. Instead, it fragments into smaller, denser clumps, each destined to become an individual star system. These dark, opaque pockets of gas are known as Bok globules, and within each of them, the process of collapse accelerates. At the heart of one of these fragments, a dense, hot core materializes, known as a protostar. This is the embryonic stage of a star. It is not yet shining through nuclear fusion, but it glows with a deep, ruddy light, radiating away the intense heat generated by its ongoing contraction. The protostar is shrouded from view, hidden within a thick cocoon of infalling gas and dust, a cosmic veil that only infrared and radio telescopes can penetrate. Surrounding the nascent protostar, a flattened, rotating structure takes shape, known as an accretion disk. Matter from the parent cloud does not fall directly onto the protostar, but instead spirals inward through this disk, much like water circling a drain. This process feeds the growing protostar, steadily increasing its mass and density over tens of thousands of years. During this phase, the system can be quite active. Powerful jets of gas, channeled by the protostar's magnetic field, often erupt from its poles, blasting out into space at incredible speeds. These jets, called bipolar outflows, act as a sort of cosmic pressure release valve, carrying away excess angular momentum and helping to clear away some of the surrounding material, offering the first fleeting glimpses of the stellar infant within. As the protostar continues to accrete mass, its core becomes ever hotter and denser. The immense pressure strips electrons from their atomic nuclei, creating a superheated state of matter called a plasma. The temperature climbs steadily, from thousands to millions of degrees Kelvin. Eventually, a critical threshold is reached, a point where the core temperature and pressure become so extreme that a new and powerful process can begin. At approximately 10 million degrees Kelvin, hydrogen nuclei, which are single protons, are forced together with such violence that they overcome their natural electrical repulsion and fuse to form helium. This is the moment of ignition, the birth of a true star. The energy released by this nuclear fusion creates a tremendous outward radiation pressure, a force that pushes against the relentless inward crush of gravity. When this outward pressure perfectly balances the inward pull of gravity, the star achieves a state of equilibrium, and its long, stable life on what is called the main sequence begins.